if we have bad weather or somebody's sick or something, you can actually join in with the class from home if you need to, and it'll be there. So let's talk a little bit about Lewis structures. I know we did a lot of work on this I guess 2 weeks ago now, because I didn't see you last Monday. But it's an important basis to how we're going to talk about organic structures, so it's good that we spend a little bit of time on it. So what kind of structures did you get for N2H2, this first one here? Anybody feel confident about it or not? Just want to throw something out there. Yeah. So like that?
No,
oh, H2, I see. Yeah. Yes, you're right. So just like this. Okay. Double bond in the middle. Like that? Okay. Anybody get something different? Okay. So let's draw that one too. So like this. Like that? Okay. Anything else? Okay. Well, first, when we look at these structures, these are both, I think these both have the right number of electrons, right? So we've got 5 for each nitrogen, that's 10, plus 2 for the hydrogen is 12. So 2, 4, 6, 8, 10, 12 on the first one, 2, 4, 6, 8, 10, 12. So they both have 12 electrons, so that works. What is the other check then that we need to do to make sure that these are good structures? Right, we need to follow the octet rule. So no atom can have more than 8 electrons. Hydrogen can't have more than 2. Hydrogens look good in both structures, they just have 2. Let's check the nitrogens. So this one has 2, 4, 6, 8. This one has 2, 4, 6, 8. This one has 2, 4, 6, 8, 10. So that's a problem. Everybody see that? 2, 4, 6, 8, 10. Too many electrons are on that nitrogen, so that's not going to work. So that first structure seems to work out, follow the rules. Should it have any formal charges? See any formal charges needed on any of those atoms? How do we calculate that? Yeah, close. It's the number of valence electrons minus the number of bonds minus the lone electron. So nitrogen has 5 valence electrons minus 3 bonds and 2 electrons is 5. So 5 minus 5 is 0. So no formal charge on anyone there. So it looks like that's just going to be the structure. And that's it. Okay? Okay, we'll move to these next couple. Now these actually help us out a little bit because they tell us how this thing is supposed to be connected. When we draw organic structures, we talked a little bit about this last time, we don't always just lump all the same kind of atom together, like all the carbons and all the hydrogens. We spread it out a little bit so we can see how the things are supposed to be connected. So in this case, this tells us that this carbon has these 3 hydrogens on it, this carbon has this hydrogen, and the 2 fluorines. So before we even, well, we can still come up with our electron numbers and all that kind of stuff. Or we can use a little bit of a shorthand and try to see how this is connected. So these 3 hydrogens must be connected to this carbon. That's what CH3 tells us. And then these things must be connected to this carbon. The way we know that is we know that those things are next to that carbon, and we know that hydrogen has to have 1 bond, and that fluorine also usually is connected to 1 bond. So we can use those as shorthands to help us out here and come up with a structure that looks like this. And then if we want to count up all the electrons, we can add those in. So we might have like this. and that's actually the structure for that one. Again, no formal charges here. So this is kind of part of what I was getting into last time, where the organic structures, once we practice them, maybe not right now, but once you get some practice, end up being a little bit easier than finding the inorganic Lewis structures, because we know that carbon's going to have 4 bonds and hydrogen has 1 and fluorine has 1. And the way that the things are written, it kind of helps us put it together in the right way. So we don't have to just start from nothing and put these things wherever, it gives us too many options. So we cut those down a little bit, make it a little bit easier. What about this last one then? H3CCN. Any ideas here? Yeah. Okay. So like that. And then we just fill in these 3 hydrogens here. Okay. How do y'all feel about that? Good? Right number of electrons? Yeah, right number of electrons. Everything has an octet. No formal charges. So that looks good. Again, we see this time it's flipped a little bit. Well, that happens also. The hydrogens come before the carbon, but that still tells us that those 3 hydrogens are going to be on that carbon, and then it goes CCN connected in a row there. How'd you come up with the triple bond part?
Well, I would have had like a pair on the end and a pair on the C, so I figured if I'm gonna have that, I could just put one.
Right, so let's look at what would happen if we tried to not do it. So did anybody get in trouble here? Did anybody not see that it was going to be a multiple bond and then start putting electrons in and realize that it didn't work? Did you get that? Yeah. So that's let's say we were doing it that way. So we figured it was going to be like this, but then didn't know what was going to happen, and we knew that there were 6 more electrons to go. So we'd go like 2, 4, 6, but now that carbon doesn't have enough electrons. Or we go 2, 4, 6, but then that nitrogen doesn't have enough electrons. So if you get in that situation where you just don't have enough electrons to spread around to actually get everything its octet, that's your clue that it's time to start thinking about those multiple bonds, to share those electrons among different atoms. Then it'll work out. So if instead we share those 4 electrons like that, we can make everything work. Okay. All right, let's look at the Lewis structures for sulfate then. So what's a Lewis structure for sulfate that satisfies the octet rule? What does that look like? Just like that? Okay. Now we know that this ion is a 2- ion overall. So that means we have to have some formal charges at least. So if you make an ion like this, that's good. Everything does indeed fit the octet rule. What do the formal charges look like? Yeah. Yeah, each oxygen is going to be -1. And that would be 4-, so then we know the sulfur has to be +2. Because remember, sulfur has 6 valence electrons minus 4 bonds is 2, so 2+. Now we almost never see formal charges more than 1. So we know there's something a little bit weird here, but that is the right structure. It happens, and there's no choice. We can cut down on those formal charges a little bit if we violate the octet rule. So we're sort of always choosing here if we want more formal charges or if we want to keep the octet. So how do we do it? How do we cut down on those formal charges by violating the octet rule? Yeah, so we can make double bonds on 2 oxygens, leave the others single bonded. Oops. And that means we need fewer electrons on the double bonded ones. and more on these. And now if you go through calculate the formal charges, only these two will carry formal charges. The others will all be neutral. Now the problem, or not a problem, but this one violates the octet rule because sulfur has now 12 electrons around it. But that's okay because it's below the second row. So either of these Lewis structures are okay Lewis structures, left or the right. It just depends on what you're going for here. The one on the right is more commonly drawn because of the lower formal charges. Okay, and we're going to talk, we'll look at this next part, and then we'll talk about what this means and what the relationship is between those in a minute. All right, and finally, CH3NO2, which is known as nitromethane. Anybody get a structure for this? Did we get this far? Take another minute now that we've gone over a little bit and see if you can come up with a structure. Let's see if everybody can come up with a structure for this one. And don't forget the formal charges as well. We got something? Yeah? Do I feel like drawing theirs up here? Yeah, come on up. Yeah. On the computer. Just draw right here. And the back is the eraser. All right, thanks. What do you think? See some head nods. Anybody get something different? 100%? Draw it. We'll do it in a different color here. Let's see.
That's right.
It's all right. Let's look at a couple of them.
I'm just putting all my wrong answers, right and wrong answers out there. Okay, so just
Yeah,
over
wherever
here.
you have space there. Okay, so similarly connected, that's good. So everybody's reading those formulas right, connecting things well. What's different about these two? Yeah. Okay. Is that a problem? Okay, so this has the right number of electrons, but this nitrogen doesn't have enough here, right? And we need an additional one. We can't just add more electrons because there aren't enough in the structure, so we have to bring a couple of these down here to make that double bond. So this is probably a better structure. Is this a complete structure? Is that just good? Formal charges, right. So I think the structure is right, but let's add the formal charges. What kind of charges did you find? Yeah, so we're going to have a positive on the nitrogen and a negative on the oxygen. So the overall charge of this molecule is actually 0 because the plus and the minus cancel out. And just looking at the formula doesn't necessarily have charges in it. But when we look at it, we calculate it out, it does. And this is another one of those areas where it really just takes practice. If you've done 50 of these Lewis structure problems, you start to realize every time you see a nitrogen with 4 bonds, it's got to have a positive charge. Every time you see an oxygen with 1 bond, it's got to have a negative charge. There are these ones that just keep coming up over and over again. So yeah, at first you have to go atom by atom and always be calculating it out with that formula. But after you do it a bunch of times, you'll just get used to it. So I encourage you to do that. Go through the homework in the back of chapter 1. There's a million of these so you can practice that way. But yeah, this looks great. So let me continue with this then. What if I drew this like this? Very slightly different. All I've changed is where the double and single bond are. So are those different or are those the same? How do you know? Yeah. Right? So it kind of seems like they're the same. They're actually not quite the same. There's something called resonance structures. So the relationship between these things is that we call them resonance structures. What that means is that let's imagine that this oxygen had a little label on it somehow. That we could see this as O1, and we could see this bottom one as O2. I mean, there's definitely a difference between O1 and O2. Let's say I guess we haven't done infrared spectroscopy, but we will do that. Has anybody done that before in other classes? I don't know if you've looked at those before, but it's a type of a measurement where we can actually see if there are single bonds or double bonds. So in both of these structures, it looks like there's 1 single bond to oxygen and 1 double bond to oxygen. But if we measure this chemical, we find that that's really not the case. We don't see double bonds and single bonds. We see kind of an average of like 1.5 bonds. And so what they used to think was that what was happening in this structure was that these two things were flipping back and forth. Like the double bond was on one side, and then it would flip to the other side, and it would flip back and forth really fast. And that's where the term resonance comes from, like going back and forth at a particular frequency. Now we know that's not really the truth. That's not really happening. It doesn't flip back and forth. But what does happen is the overall structure of nitromethane is actually a hybrid of these two. It's like an average of these two. So if we do some analysis and actually measure these compounds, we find that the nitrogen-oxygen bonds in these come out to about 1.5 bonds. So they're like in between a single and a double bond because it's an average of the two possibilities. And that's what's known as resonance structures. So in these organic molecules, when we draw resonance structures, what we're really saying is how can we move the electrons around without really changing anything in terms of connecting things up. Another example of that, which we didn't talk about, or we didn't say, but is the same thing, is these two sulfate ions. So you'll notice these two sulfate ions are connected in just the same way. The only difference is that in order to go from this structure to this structure, we take 2 of these electrons and we move them down into a double bond. And then we take 2 of these electrons and we move them over to a double bond over there. So we end up with 2 double bonds instead of 2 single bonds, but we haven't really changed anything about the overall connectedness of the structure. We've just moved where the electrons are. And whenever you do that, whenever you just move electrons around without changing anything else, those structures are known as resonance structures. We'll see some more of those as we go. All right, so how do you feel about Lewis structures so far? Okay? Looking pretty good? All right. Well, we'll keep practicing those, and we're going to extend that now and do a little bit different thing with them. So I have one more thing to pass out. And then I'm also going to ask you to just take one of these and pass it around. You can take the big kid or the little kid, it doesn't really matter. And don't start in with the activity just yet. We'll talk about something else first. But just so we're all ready. We'll pull this thing up here. Models. So who has anybody ever used these things before? Model kits? Just for fun? It's just what you do for fun, right? No? Yeah, just in your free time. Have you used these specific ones? Does anybody have these specific ones?
Were we supposed to get these
You know,
on like the thing? I got it just because it said.
Yeah, I think it's a good idea. I don't think it's required.
I think it said required.
Does it say required on there? The little one, right? The smaller one? Yeah, it's not too expensive. Yeah, I mean, I would recommend a model kit of some sort. As you'll see, we're going to use it a lot to visualize these structures and what they look like. So it's a good idea. But let me take you through this a little bit. You don't have to get this exact one. There's another style that I really like, especially for bigger structures. I'll grab one of those too. Oh, yeah, that's the one. These guys are a little bit cheaper. You can get them on Amazon. They don't look as pretty, but they are a lot faster to build things with. So let's look at how these things go. All right, take out a little black ball. Can you all see me if I kind of just do this, or do you want me to put it up on the camera?
What's that little white thing? That might be where they broke.
They broke off, yeah. Grab one that doesn't have those stuck in there. You got one. Somebody was extremely violent with your model set there. You can grab another one if there's no clean. All right. These little black balls represent carbon atoms. You'll notice they have 4 little holes in them. And the holes are kind of at unusual angles. It's almost like a cube that got its corners cut off. So that's exactly what it is. It's a cube that got its corners cut off. And so grab these little sticks. It doesn't matter what color sticks you use. I know some of the kits have different colors, but try to find 4 of the same color and about the same length. And put them in those 4 holes so we can take a look at it. You got that? Okay. So who remembers from general chemistry what the shape is called? Tetrahedron, right. Very good. Anybody ever heard that word before? Yeah. So tetrahedron is this kind of symmetrical 4-sided shape. We can draw it. A tetrahedron itself is actually a solid. It's called a regular solid, which means all the sides and faces are the same. It's kind of like a pyramid with a triangular base, all equivalent sides. That's really what a tetrahedron is. But we call this a tetrahedron in that if the carbon atom were in the middle of this shape, kind of floating in the middle there, and then we connected things to the corners of that tetrahedron, we would have the same shape. So that's where this comes from. Another way of visualizing that is if you imagine a cube. Let's see how well I can draw a cube of this thing. Everybody knows what a cube is? Looks like this? Okay. So if you imagine a cube, a tetrahedron kind of comes from a cube. If you, again, put that atom in the center and connect it to opposite corners on each side. Let me also, these are the back, that's the back part of the cube there. Okay, so that's where the tetrahedron comes from. I don't know if that makes it better or just more confusing, so ignore it if it's more confusing, but that's what this shape is. And these angles are about, remember that number? Yeah, about 110. They always say in these books 109.5, and I know everybody always remembers that. It's kind of a silly thing to remember. Yes, it's true that in methane, which is CH4, those bond angles are exactly 109.5. But in pretty much every other structure, they're going to be a little more or a little less depending on the structure. So I don't know why we don't just round it and say it's about 110. So I always say it's about 110. If you like 109.5, that's fine. Call it 109.5. But that's the angles here. Why do we talk so much about this? Well, as we'll see, when we start to build up these structures, it's going to actually change how we draw this thing and how we look at this. And we're going to look at a new way of drawing structures called line structures. So let's look at the beginning of this sheet. And it tells us to build a model of propane. We might get to names today a little bit later, but propane is C3H8. So we've got 3 carbons and 8 hydrogens. So everybody build a model that involves 3 carbons and 8 hydrogens. There's only one way to do it. In these kits, these little tiny white balls are the hydrogens. A lot of times we're going to leave them off, but today we're going to use them. When you do build these things, I always recommend building the carbons up first and then adding the hydrogens later. If you need more pieces, if you grabbed one of the smaller kits or if you've got a lot of stuff missing, there's plenty more here you can grab if you need. But let's build that C3H8. If you really want to be fancy and you want to make like a different color bonds for the hydrogens or something, I don't know. People get into it. It's up to you. Isn't this fun? You get to come to school and just play with toys. My kids would be super excited about this. If they knew that this is what we were doing right now. They would be jealous. So then the younger one would probably eat one of these little things and then I'd be looking for a little plastic ball and a poopy diaper, so probably not a good idea. Got some nice models? Looking good? Okay, notice some things about the shapes here. So first notice that you can kind of spin these things around. That is reflected in reality in that single bonds can rotate. And so there are various different forms that we could kind of imagine this being in. It could be in this very symmetric orientation. It could be offset a little bit. You could line all the hydrogens up like this. There are various ways that we could twist this around. But we're going to focus first on what we call the most stable or the lowest energy conformation, which is known as staggered. What do you think it means for this to be staggered? Yeah, everybody try to put yours in what you would consider a staggered orientation and show me. And hold it up and see what you think. No idea. I'm purposefully not telling you what that means. So you can guess, and then we'll talk about if it's right or not. Yeah, what does staggered mean, like in real life? Like uneven?
Yeah, like not lined up exactly.
Yeah, kind of like
Kind of
one and then
squeezed
the other. Yeah, that's right. So in chemistry terms, or in the terms of this molecule, when we talk about staggered, we're saying that if we look down this bond like this, you see how these things are lined right up? That's not staggered, so that's staggered. Where these two kind of are split by the back one, and then this one's split by the others. And then if we look at the other one, the same thing. So actually, I saw a lot of you put this in that orientation to start with, just because it kind of looks nice. You can see it kind of going up and down. This is the orientation that will sit nicely on a table. Okay. Staggered orientation is the one that kind of just sits nicely on its feet. And if you look straight down the bond, like you're directly in line there, you can see that the one in the front kind of splits through the ones in the back of that bond. Can you see that? It almost looks like a six-pointed thing if you're looking straight down the bond. And then you flip it one more time and you look down the other bond, so you're going from this to this, and you see the same thing. And that's what's known as a staggered orientation. So now our trick is to draw this thing in this orientation in a way that makes it clear that it is indeed in this orientation. And that's maybe not obvious how to do that. So let's take a step back and look at how we're going to draw each of these, and then we'll build up to that. Okay, so we go back to just the single one. If you don't want to build a whole new single one, you can just pull one off of your three. We'll put it back together in a second. So we have to find a way to express this shape, this three-dimensional shape, in 2 dimensions on the paper, but still convey the information that we need to convey. So here's how we do it. I'm going to draw this carbon in the middle. Okay, that'll be our starting point. That's the carbon. Now, if you hold this like this, what you see, and hopefully you see this also, is that the way I'm holding this line coming up and this line coming over to the side are in the same plane. They're flat with each other, right? Everybody see that? And then if those two are flat with each other, then this one is kind of coming back toward me, and this one is going out toward you. Everybody see that? All right. So now, the way we draw that on paper is the ones that are flat in the plane, which is going to be the top and to the left, your left, we're just going to draw a straight line, top and to the left. And that shows those staying in the plane of the board or of the screen there, staying in that plane. So then the two on the right are one's coming out at you and one's going back, and they're directly in line with one another. Like if you close one eye, one of them is covering up the other one. You see that? If you can't see mine, maybe you can see it on your own. The way we express that is by drawing this kind of a shape for the one that's coming out at you, and this kind of a shape for the one that's going back. We call this a wedge. That's the one that's coming out. And we call this a dash or hash sometimes. And that's the one that's going back. Now we can't draw them directly on top of each other or we wouldn't be able to see both of them. So we offset them a little bit. But when we see that notation, we know that they're actually right exactly in line with one another. They're not offset like we see them in the paper. They're right in line, just like when you hold that thing up, that shape up. So this is called dash wedge notation or 3D notation. And when we want to convey the three-dimensional structure of an organic molecule, this is the type of notation that we use. When we get in a couple of chapters from now, this is going to get more complicated because there can actually be differences depending on for more asymmetric structures. We'll get into that when it's that time. For now, we're going to use that to express this structure that we've just drawn. All right, so let's go. I'm just going to stay up here because I have more space. You can do it in your sheet if you want, or you can do some scrap paper first. Well, let's go back to our staggered structure and think about what that means in terms of the notation that we've just talked about. So to make things easier on ourselves, we're going to take our carbon chain, our carbon-carbon chain, as being in the plane of the board. So if I'm holding this up, if you've got yours just like mine, that means that this hydrogen, carbon, 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 hydrogen, those are all in the same plane. Those are kind of in a zigzag. You see that? And then the other hydrogens we can see, one is coming out and one is going back. Coming out, going back, coming out, going back. Everybody see those? So that allows us to draw this whole thing in a three-dimensional notation that looks like this. So I've got carbon on the right, or on the left, sorry, carbon on the left, carbon in the middle, carbon on the right. Then I've got the hydrogen over on the right and the hydrogen over on the left. And then the other hydrogens will be occupying dashes and wedges. And does it matter which one we put on the dash or which one we put on the wedge? In this case? It doesn't, because they're just the same. If we had one, like a bromine on one and a hydrogen on the other or something, that will start to be different, and we'll get to that. But for now, it doesn't matter. So on each of these carbons, we're going to draw a dash, or a wedge and a dash. To represent where those hydrogens are. And this is what we would call the 3D or dash wedge structure. Okay. Everybody with me so far? Maybe. We're actually not going to go on to the right in this now. I mean the other boxes. We're going to go down, and we're going to look at the other three-dimensional structures, and then we'll talk about some other ways to draw these structures. So for the next part, we're going to replace, I'm going to ask you to replace one of your hydrogens with fluorine. And to show that, just pick another color, blue or red or something. I use green. How about green? That's nice. There are two different ways that you could replace a hydrogen with fluorine, which would be C3H7F. There are two different structures you can make. See if you can find both of them. And then see if you can build those and draw them in the same way we just did in that three-dimensional structure. Remember, you're not replacing a carbon, you're just replacing a hydrogen. You still have 3 carbons. Yeah, on to the next one. Build 2 structures that exist for the formula C3H7F, meaning that we're losing a hydrogen and gaining fluorine. There should be 2 different ways to do that. And then see if you can draw the 3-dimensional structures for each of them. So they'll be very similar. I mean, they'll look just like what we just did, but have a fluorine replaced with a hydrogen. See what you can draw. Can anybody figure out what are the 2 different structures you can have here? Everybody, looks like everybody has 1. How's yours different? Right. So I don't know. We all saw that. So if you're having trouble finding both of them, there's only 2 different places you can put it. You can put one on the end, that, or you can put one on the middle. Why is this not different from, like, if I put it on this one? But yeah, they're kind of the same because, like, they're related by rotational symmetry. Meaning, if I put this one over here and I rotate it, it could be over here. So any of those positions are going to be the same because this thing can rotate freely. The only time that they're completely different is if we put one in the middle. Then it's no longer in the same spot. There's nothing we can do to rotate these to make this go onto the end. You have to actually disconnect it, put it somewhere else.
That's right.
Yeah, so that's one, and then the other one's on the, yeah. All right, how do these look? These structures look really nice, by the way. Just, a couple of years to work on the second one, so another minute or so. Yeah. So the other question here, let's say I made this one. Did anybody draw that one? With the F coming out of you? So is that different from the F being in the back? Are those two different structures? Why not? How could I turn this one into that other one where it's in the back without, yeah, so if I just flip it around like that, now it's in the back. So those must be the same. So it wouldn't matter where you drew it in that case. So there are a bunch of different ways, there are a bunch of different correct ways to draw these different structures. Again, I can probably fit it into here now. Just zoom in a little bit. So we'll start with our basic structure here. And I notice a lot of people put the F on the end here. That's fine. You could also put that F on either the dash or the wedge. It doesn't matter. Anywhere on that carbon is going to be one of those structures. Also, I noticed almost everybody, I don't know everybody, almost everybody put it on the right side. It could also go on the left side. That's the same as well, because you could flip it over and it would be the same thing. And then the second version would be the one where it goes in the middle. Again, on the dash or the wedge, doesn't matter as we just demonstrated. All right. Anybody know what the relationship between those two molecules is? What are those called? These are called isomers. Isomers are molecules that have the same molecular formula but a different connectivity, meaning they're connected in different ways. So in these two structures, they're absolutely different structures. And when we get into some of these properties, we'll see that they'll have different boiling points, maybe different reactivity. They'll be totally different in behavior, but they have the same molecular structure. And so with this, or the same molecular formula. So the same number of carbon, hydrogen, and fluorine, but because they're connected in different ways, we call those isomers. And one of the trickiest parts about isomers is that like if I say draw all the possible isomers of C3H7F, there's only two of them, but there's a temptation to kind of put the fluorine every possible spot. And the tricky part is recognizing which ones are the same and which ones are different. So we'll get into that a little bit soon. Okay, so we're going to skip that bottom part for now. We'll come back to it. Did you have a question?
Oh, no.
Okay. Flip the paper over to the back. And then see if you can do the first two boxes, the Lewis structure and the 3D structure for butane, C4H10. So we got to have now 4 carbons in a row. Use your models to help you. And see if you can draw a similar structure to what we've just been doing, but now with an extra carbon and more hydrogen. See what you can come up with. Yeah, you can use the models in the test. It's another reason to get your own. You can like draw notes on the models in tiny little letters. Now don't actually do that. That would be cheating.
If I could write that small, it would be great.
You'd also have to be able to see it though, which would be.
The magnifying glass.
Yeah, you could replace one lens in your glasses with like a magnifying
Yeah, and
glass.
then you guys would be looking at me.
You're like with like this during the exam.
Yeah.
It'd be very sneaky.
It's a new prescription.
Has anybody ever cheated in a particularly clever way?
What I've heard ways.
Yeah.
And then like inside of like their water bottle label.
Well, actually, the sneakier way to do that is to use Coke or something because it's dark and it covers it up, and then you only see it when you take a drink. Because you can't, right? Because the Coke would cover up the inside.
Yeah, like
We've seen some different ones. Oh yeah, yeah, you can do that. So it just looks normal with the nutrition facts for the formulas. I've seen some of the least creative ways to cheat in my classes. I had an exam once where somebody literally held up a sign to other people on their scrap paper. Like they wrote, "What is number 2?" And they wrote like this. And I was just sitting there like looking, staring at them. And they were like, for them.
Really?
Yeah.
Wow.
In high school, my best friend in her world history class, literally everyone cheated. Like it was the first class that anyone took to get into high school. And she and her friend made up Morse code for different letters. Like,
There is a Morse code for different letters.
Like
They made up a new one?
Made up their
Well,
own.
no, like they made up their
Oh.
own, like A, B, C, D, whatever. They like
Okay.
tap.
People put a lot of work into like.
Right.
Yeah.
Like, you're so smart. You're coming up with ways like that.
Right, just put in that much work at actually learning the things.
I've only cheated once, but that was in high school. Like somebody went in the teacher's office and stole the final.
Oh.
And then you got the whole class got A's. Zero and the answer.
Wow.
Final.
And it was not suspicious, like the teacher wasn't,
No.
didn't raise anything like, oh, I must have been great. And they all passed.
It was for a science class. It was definitely science.
If everyone in high school got an A in a science class, the teacher would like knock it out right away. There's no way that everyone would get an
Yeah, I think that just depends on the numbers. Like in a class this small, I would not be concerned if everyone got an A because you can't expect 7 people to have like a perfect distribution. But if I was teaching a class of like 100 people, then it would be a little bit. Anybody have some nice butane structures yet? Let's see some good models.
Can things be connected to your drawing? Like, yeah, we have everything on a plane for
Mhm.
the HCC, then when you're doing like a wedge, let's say, I put a C on it and then we'll attach hydrogens to that wedge C.
You could. There's nothing wrong with that. Usually the convention is if you have a bunch of carbons in a row, you keep them all on the straight bonds. Ah, yeah, you found a different one. So that's actually for here. But as long as you got it, yes. So you're absolutely right for that model. One of them needs to go on the dash or on the wedge. So you're just ahead of the game here.
Okay, so I can
But,
draw it the regular way.
But the regular way would be then. The first one was keeping them all edge. You got a little.
Alright, okay, wait, now I have to figure out how to build that one.
So nice.
I just really move our class, and she's like, when we don't understand answers, we'd be like, oh, can you help us with my situation, sir? Come back with the answer A, then to B, then to D, just because all the answers were like that.
That's nice.
Yeah, but stretch it out a little bit.
My sister, who would give me answers?
Like spin it around so it's a little more stretched out and sits on the table nicely.
Build.
So as you've noticed, when you get that fourth carbon in there, there's a lot more options for how you're going to actually arrange it, right? That's called degrees of freedom. But just like different ways you could rotate it, you could kind of have these things where the hydrogens are really close together. What? Yeah, it looks like a pentagon. You can kind of stretch it out so they're further apart. Any ideas what would be the better way to go with that? Any ideas, like if you wanted to guess what you think a butane molecule looked like just in its normal state, sitting around somewhere in a butane tank, in your lighter or something, do you think that the hydrogens would try to be as close together as possible? Why?
They push off the reach.
Yeah, they'd repel each other. Why? Close, but the opposite. Negative, right? Because let's think about the structure of the atom. Way back, general chemistry. You've got the nucleus in the middle, positive protons, and then all around the outside are the clouds of electrons, which have negative charges. So atoms, when we talk about them like this, they aren't really connected by these long sticks. They're these big spheres that are kind of mushing together. So they're big spheres of electron density, which means they're going to keep as far apart from each other as they can. That's why all those geometry rules work, like the tetrahedron and everything, because the electrons want to push each other away as much as possible. And that's true for these bigger structures too. So we don't expect to see something like that. That's going to get in each other's way and really have some repulsion. So the more we can stretch this thing out and get everything out of each other's way, the more stable that structure is going to be. Similarly, we're going to want each bond to keep that staggered conformation. So when we look straight down each bond, we want to see that same shape where each one in front kind of splits two in the back, or each one in back splits two in the front. And as we keep going through from bond to bond, we see that same thing each time, no matter how we look at it. If we're looking straight down one of these bonds, we see that nice geometry. That's also going to always allow it to sit nicely on the table, on your hand. Right? That's going to be that staggered geometry. Okay, and as stretched out as possible. Right, so once you have that fully stretched out, staggered geometry, try to draw it. See what that looks like. You should set it up so that there's, again, a chain going down the middle that has everything in this nice zigzag line in the same plane, and then the coming out and going back are at the top and the bottom coming off. See if you can draw it like that once you've got it in that position. So this here's
Just try it as a line, and we do it as coming towards us. Like a wedge.
right. So in the worksheet part, on the first block is just a Lewis structure. So that just means kind of draw everything like 90 degrees. But then the 3D structure, what we're more interested in, right, like you got it. So you got this lines going across. You imagine a straight plane cutting the thing in half. Anything in front of that is going to be on a wedge. Anything in back is going to be on a dash. Yeah.
So it's okay to draw them like on a gas. So like if you did the dash on this
Well,
like wedge on the dash.
right. I guess it potentially could be like that, but if you look at the structure, it wouldn't really make sense because it's that way, both from the bottom. So it makes more sense to draw just opposite. So you're going to think about your lines. This. Those are the coming out from that. Those are just going to stick out on that. So it's very fun. Yeah. That. yeah, that's right in the middle. Maybe
So you're
rotate
looking
it around.
this way. So you're looking at that and then see this.
Go straight down.
No, like this. So you see what this is. Right, like coming up, no, that one. So you look down,
We'll get to that in a minute. But there's another way you can actually use the same
this one, no, this one.
pieces to make it completely different.
Okay, which you knows.
Not just like that. Yeah. So everybody's got some nice drawings here.
I switched.
Okay.
So I screw it there with it.
Yeah, that's fine.
I already made my best again.
All right, so I'll skip the Lewis structure for now because I think we can all do that. But let's look at how mine is set up here. I'll just follow that, and it looks like yours look about the same. So I've got the 4 carbons kind of going up and to the left, then down, up, down, over to the right. So I'll keep that same shape here. Okay. And then I've got those hydrogens coming off. Like this.
And you can put those wedges in the meshes.
Not exactly.
Like, what I mean.
Oh, you mean like on the left or on the right? Yes. Right, that doesn't matter. Those will be the same. Yeah, and you can put dash or wedge on the left or the right. That doesn't matter because they're supposed to be directly in line. What you do want is make sure that they're on the correct side of the chain. In other words, when we look at that structure, we know there's nothing down here, nothing up here, in those kind of spaces. So we wouldn't put one of the dashes or wedges in there. We would keep them on the outside of that, that main chain. Otherwise, I think we're okay there. Okay. Last thing we'll do, and then take a little break, is look at an isomer of butane. So this is what we call butane, which, by the way, is the same stuff that's in a butane lighter, which you can't use to smoke on campus anymore, but perhaps you've seen one in the world. There's another molecule that has these same pieces and that you came up with kind of accidentally instead. There's another way you can arrange these pieces and make a totally different structure. And I don't just mean twisting them around, because we know twisting around still means the same thing. That's still the same structure, it's just twisted around in a different way. You actually take this thing apart and see if there's a different way that you can connect these pieces that makes a totally different molecule that you can't stretch out into a 4-carbon chain like this. Yep. Put that down so nobody else sees it. See if you can come up with it. And then when you do, see if you can draw it. Remember, your carbons still have to have 4 bonds. Your hydrogen still has to have 1 bond. So you're going to have to take a couple things apart to get some space to do that. Yes.
Actually, no, I know I didn't because I'm missing.
Yeah, so this carbon, when we have it, this carbon's 5 bonds. 4, just put this in a different position.
Breaking my models.
Think about what's not right there. Right, so it's hard to draw that three-dimensionality of the right? But what I would do is keep that hydrogen on.
Oh,
Because that's the thing. The way you have it drawn really is like this. Right? Because you've got this
Oh,
carbon
yeah.
out there.
Yeah.
That hydrogen.
Okay.
Yeah.
So this
Right. That's right. That's right. So,
So this
the
has
way
to
you
be-
got it out of here.
Yeah.
Uh-oh. Sorry. That's the same thing. That's right. Yeah.
Okay, how about this?
Yeah, that's how you do those doesn't really matter in terms of national budgets, but what I would say is if you look at this like that, you've got this thing in the back from the dash. So the hydrogen should be forward like that, and still have a nice size. So it's just like over here, the dash and the are always next to each other. So, you're getting too fancy with extra blue pieces there, or you just have one.
Oh, no, I gave up on it.
Okay. Yeah, this is maddening to some people, like trying to find all the different possibilities. When we get up to 5, 6, 7 carbons, and there's a bunch of different possibilities, then it'll get really fun. So that is interesting. So what's wrong with that? Yeah, hydrogen can't have more than one bond. All right, so let's look at how this would actually work. The only possibility here, and a few people got it, is to actually switch this whole carbon with 3 hydrogens group with one of the hydrogens on the middle carbon. So taking that off of there and putting it there and making this kind of an arrangement. This is the isomer now. Okay, so now let's talk about how to draw this. Oh, I should also, so let me tell you the shortcut that I didn't tell you before, because I just wanted to see everyone struggle with it. It's good, it builds character or something, I don't know. Anyway, when you're trying to find these kinds of things, the easier way to do it is to ignore the hydrogens at first. The hydrogens are what's distracting. Different isomers are all, assuming that they are not other stuff like fluorine or whatever in there, but different isomers of carbons are always going to have the carbons connected in a different way. So if we just looked at the carbon chain like this, and we said, well, what's a different way that these could be connected? And we start playing with it, it would probably become apparent a little bit sooner that that's really the only other possibility. It's when you have to switch them with the hydrogens that it gets tricky. So that's really my trick here. If you're looking for isomers, just look at the carbons. Even if you're doing it on paper without models, just draw the C's in a row and then think about how you might connect them in other ways without looking at any of the H's, and then put in the hydrogens later and make sure that you still have the same number. So let's look at how to draw this, this kind of a structure. The way to do this is to think about it like the propane that we drew earlier. So we're going to think about this as the same as the propane. So if I cover this other part up, that's that same propane we drew earlier. And now we've just got this extra thing coming off one of the propane parts. Wow, that's special.
It's really something.
Looks like some kind of crazy airplane or something. Helicopter. Okay, so let me draw this so you can see it. At least, and you may have something slightly different, but we're drawing basically what is a propane structure that we drew before. But we're going to replace one of the hydrogens on that middle carbon, with another carbon. And the way I've got it here, that one is on a dash, but it doesn't matter. It could go either way. And then there's going to be 3 more hydrogens here. Usually once we look at that branched chain, we no longer worry about the dashes and wedges because it just gets too confusing. It doesn't really make sense how you would say something is in the same plane or going once the thing is already back there. So I just draw them all as lines when we get to that point. It's only in that main chain that we're looking at we're going to be drawing the dashes and wedges. And then in a minute, well, when we come back, we're going to look at a shorthand that's going to take some of this out anyway. Yeah, so the Lewis structure, we kind of skipped those. Lewis structure, we just wouldn't show the geometry, so it would look kind of like this. I mean, it's always okay in a Lewis structure to show the geometry, I think, but what this was trying to show here was just that you go from here to that, and that's where that kind of comes from. So we've got some of those things down. Let's take about a 10-minute break, grab some food, try to rest your brain, try to turn it off for a second, look at something stupid on your phone so you can be ready to think some more, and we'll get into some more things. Build some nice shapes, yep. And then we'll be ready to continue. Grab a snack. So we'll start back up at about 6:35.
I felt like Morning Girl was gonna like jump out. Seriously, there was like no one there. The dryer is really, really loud. It's dark. That one recording. Yeah, that one is. During the day, it's like fine, but.
Everybody's brains reset. There's more. Yeah, get there. Yeah, this is a really, I don't know if you've done this before, but this is a really difficult way to take a class. This, like 3 hours of class stuff and then the 3 hours of lab stuff. Makes it tough because we're basically doing a whole week of chemistry in a few hours, and by the end, everyone kind of just gets worn out. So the way to make sure that you can do it properly is just keep with it all week. Make sure that you're always going back to the book, that you're doing practice problems, and that this isn't the only time that you're working on this stuff. That way you'll keep up with it, because it's easy to just say, like tomorrow, oh, well, we don't have chemistry again until Monday, so I'll just relax tonight and we'll work on it this weekend. That's not a great strategy. All right, well, let's continue. So everybody feels pretty okay with this type of 3D structure drawing?
I always do it.
Until you get home? Yeah.
You try to do it.
Well, the sooner after tonight that you can try to do it, the better. Like, you just go after class and do it, or pick up in the morning or something. But please let me know if you're having trouble. But we're going to extend this a little bit. As you might imagine, as you probably figured from what we've done so far, as molecules get bigger, this starts to be a pretty tedious way of drawing them. So we have to come up with a little bit more convenient, quicker way to do this. I'm going to make sure I'm doing this the same way that the book does. If you're following along in the book, I don't know if you've noticed in the syllabus, we don't quite go in the order. We're skipping the acid-base stuff for now. We'll come back to it. So we're actually looking now, getting into chapter 3 is where this stuff is that we've been talking about. And so we're going to talk about how to draw these structures in these couple ways, and then we'll get into naming and functional groups if we have time tonight. We'll see. All right. So we're going to talk about this other way to draw structures that from now on will be the main way that we draw structures. This idea of depicting them in 3 dimensions and looking at every possible thing that's connected is great for smaller molecules when we're really focused on that, but for most of this we're going to be looking at larger molecules. We need something a little bit quicker. So remember when I told you that a way to quickly kind of see the shape of the molecule was just to take all the hydrogens out? That's essentially what we're going to be doing in drawing structures. But the thing that makes it even a little crazier is we're going to take the carbons out too. We're going to take all the letters out, and we're just going to draw the shape of the molecule, and from that we're going to be able to tell everything about that molecule. The shape, the formula, eventually the name, all that stuff. And that's what we call line structures. The book calls these line angle formulas. Line structure is a little bit more common, but that's what they're talking about. So it looks like this. Let's grab our structure of propane. So we'll go back to propane with just the 3 carbons. You can just kind of look at yours from what you've got drawn so far. I'm going to hop back up here and copy this over because I have magical technology. So there's propane. Just take a look at what you've drawn before. And this is our 3-dimensional structure. Now the line structure of propane looks like this. Okay? And that if we know the rules, which we'll talk about in a second, that tells us just as much information as the one on the left does. So let's look at how we get that structure on the right and how we can know what's going on. So a couple rules of line structures. First, carbon atoms are assumed at each line end and vertex, which is a fancy way of saying connection. So anywhere a line ends or connects with another line, we assume that there's a carbon atom there. That means here we've got 1 over here, 2 where these 2 lines connect, and then 3 at this end. So those correspond to 1, 2, and 3 in the previous structure. This is where this geometry really helps us out because we have to put those angles in because that tells us there's carbon there. If we just drew a straight line, we wouldn't know how many carbons were represented by that line because we couldn't see that connection in the middle. All right, and then the second rule is that we assume enough hydrogens to fill the valences of the different carbon atoms. So we don't draw the hydrogens in there, but we know that carbon always has to have 4 bonds. So if this carbon over here on the left has 1 connection to carbon number 2, then it must have 3 more hydrogens that are not shown to get to that 4 total. If this middle carbon has 2 connections already, 1 here and 1 here, that means it needs 2 more hydrogens to make 4 bonds. And then this one again is like the front one, so it has the first one, so it has 1 connection to carbon number 2, needs 3 more to fill its valence. So keeping those 2 rules in mind, we can get as much information from the structure on the right as from the structure on the left. We know how it's connected, we know where the carbons are, and we know where the hydrogens are. But it's going to take a little practice, so we're going to do that now. Okay, third rule we should also note, it's kind of a parentheses rule, only when it applies. Other atoms are not abbreviated. So let's say we have this molecule, this is ethanol. It has an OH. We don't do anything with that OH when we make the line structure. So the carbons get abbreviated like this, but the OH stays OH. We don't take the hydrogen off of the O. So that's a common mistake sometimes, is to cut hydrogens off of everything. You only cut them off the carbons, or you only don't show them on the carbons. You still show them on everything else. Okay, so that in mind, let's go back to what we've been doing, and let's see if we can draw line structures for each of the structures that we've already drawn. So we did propane. You can fill that one in here. Right, exactly. Yep. So now see if you can draw line structures for your 2 isomers with fluorine here. And then see if you can draw your line structure for butane. And then we'll go back and do some of these other ones as well. About those rules, and it doesn't have to be right. Just put something down that you think follows those rules and expresses those structures. You don't have to do this individually either. It's not a quiz. Talk to each other, compare, and see what just don't look at the answer on your phone. That's yeah, so we don't do anything with the other atoms. We leave with that. Like when there's a fluorine, you gotta show that. There's gotta still be a bond, no line that connects the carbon to the atom. It's just the C's and H's that go away. Any C's or H's. Unless the H is connected to something else. We don't have any of those things. Right. With N, H, whatever. Nope.
Oh, these
it's
lines are
not
so easy. And then
two carbons. It's got another line up the floor. Got it. What? Okay.
This is so easy. I look like that. Oh my god.
Yeah, we'll get there. Couple weeks. So these are just the same too. You got yeah, I think you had it right at the model, but yeah, well, not completely different, but a little bit different. That's right, but what does that mean? This is sort of floating.
Yes.
There you go. But now it looks like we've got 4 carbons. 1, 2, 3, 4. The fluorine isn't in the middle connected to the different carbons. It's only connected to that one carbon.
So there's no. We got this data.
Yeah, right.
Oh. Yeah.
Good question. So the way you have it like this, it makes it look like there are 2 carbons and then the fluorine is there. Right.
And then it was kind of like took off the whole
But here we don't actually see those like that.
It's like show that it's not.
See that? Okay.
So would you show dashes or bunches coming? One's coming.
Sometimes you do. Yep. Well, we'll talk about when that is. You can, yeah. All right, so I looked around. It looks like most of you kind of talked to each other, and you got that this line structure would look like that, right? And then this one would be like that. So just to take inventory of everything, right? We've got those 3 carbons, 1, 2, 3, just like here, 1, 2, 3, and then the fluorine is connected. So when we do have that label, that F there, we don't assume a carbon at this end right here. We just say that that's got the F there. So then what would the butane look like down here? So we want to just draw it in the air. Yeah, just kind of like that, right? Right, or you could also do it like this, would be the same thing. And then we've got our branched chain over here. Looks something like that. Now you can also have dashes and wedges on these line structures. We won't see that until a couple chapters from now when we're talking about some of the 3-dimensional arrangements. Actually, I'll take that back. We will see that later in this chapter 3 when we talk about some cyclic compounds. But for now, we'll focus just on these lines. So now let's practice drawing some different structures in this way with these line structures. So we'll go back up to these 3 structures here. And we're going to draw line structures. Now, if you want to draw the Lewis structure first to kind of get it, or at least the carbons with C's and the other stuff, please do. But the point is eventually to get that line structure. So let's try that. See if you can draw a similar type line structure for each of these. Remembering now that we don't cut out the other elements. The nitrogens and oxygens we have to show, just like we did with fluorine. Yeah,
That last one is different though.
right. There. So just put it. You almost need like a little space. All right, so these look pretty good for the first two. That third one is looking a little questionable. Other ones, some of the other ones are. Which one?
Last one.
All right, let's look at these first two because these seems like you got these pretty well. So you got your propane and then this other thing sticking off, and the other thing is just as it is, and we don't mess with it. So you've got this and that. I think that's what I saw in most papers around. So now what's going on with this third one? It seems like there's a lot of discussion, debate, anger, confusion, various emotions.
Well, because we can't separate the O from the C.
Yeah, so the key here is, I think, just not to think too hard about it. Let's look at the Lewis structure and then let's just use those rules and stick that directly into line structure form. So in a Lewis structure, let me zoom in so I have a little more space to write here. The Lewis structure, we'd have the CH3 over here, and then the O, and then the C with the 2 H's, and then the C with the 3 H's. So then the line structure says, leave the O alone, get rid of the other carbons and hydrogens, and just put them at the ends or connections of lines. So if we leave that O there, and then we just put a line over here, so there at the end of that line is this carbon, and then the end of this line is this carbon, and then we connect that second one. So if we count out those carbons, we've got 1, 2, and 3. 1, 2, and 3. So it's connected in the same way that the Lewis structure is. There's nothing fancy. There's no magical floating O's. It's right in there. All we've done is we've gotten rid of the carbons and hydrogens, and we've shown that they're there by this zigzag type shape. Everybody see how that works? I think so, maybe. Again, kind of thing takes practice. There's a lot of this in the book. So we're going to look at one other way of expressing structures, and then we'll look at some bigger examples. So let's go all the way back to propane. Put this back in its correct spot here. We're skipping these Newman projections for now. We might get to those, not today, maybe some point. So we've got our 3D structure, we've got our line structure, and we've got our condensed formula. A condensed formula is not as quick or as easy to draw as a line structure. And I don't mean easy like it's easy to make, because obviously we're going to work on it, but just that it's fast. Line structures are really fast. Condensed formula is often how we see structures when they're written on in paper or in books, because it's all in one line. So you write the whole formula without using any lines or anything. You just write the letters. So something like propane would look like this. It's the formula. It's like the molecular formula, but you write it in the chunks that are connected to each other. So a carbon with 3 hydrogens on it, then a carbon with 2 hydrogens on it, then a carbon with 3 hydrogens on it. That's a condensed formula. So what might be the condensed formula for this next one, right here? That's right. So the number 3 that we just did, those were condensed formulas, right? Just written according to their conductivity. How would you write a condensed formula for this one? Anybody want to say it out? Go ahead. Yeah. CH3, CH2, CH2F. Now we need to know a little bit about chemistry to be able to interpret these. We need to know that hydrogens don't get multiple bonds, and they're actually coming off of the carbon. But other than that, this tells us the same kind of information. Like CFH2 instead of CH2F. Yeah, sure. So it could be on this side instead. Yeah. Well, we have to think about this now. It's not CH2F. It would be CH3 and then CHF, right? And then CH3 again. So we've got CH3, CHF, CH3. Okay, so let's jump down to butane. Our condensed formula would be, how would you say it for butane? Mm-hmm. Okay. Anybody have any issues with that? And where it can get tricky is in something like this. So we have to make this condensed formula different from this one. And we need to show that that CH3 over here is coming off of that second carbon. Anybody know how we do that? Mhm.
and then CH3, and then draw like the CH3 underneath.
Yeah, so there's a couple ways we could do that, and we'll show you both of them. The easier way, and the way that I think is a little bit clearer, but not always possible, is to draw the condensed formula of the main chain part, and then put that CH3 coming off of it down below. And this is what you'll see mostly in the book. This still shows you kind of the shape of the molecule. It still shows you the information you know you need, and is nice and clear, but it also condenses those hydrogens down. So that's great. There's another way to do it, which you don't see quite as much anymore, but if you really need to keep your formula in one line, like you don't want it, you can't draw lines, like if you're typing this in Word and you don't want to try to find some line thing to do it, you'd really want to just be able to type it out. And the way that's done is with parentheses, so it would look like this. All right, so this CH3 in the parentheses would be this one that's coming off of that carbon. The parentheses tell you that it still goes with the thing before. It doesn't stay in the line. So those are two ways of writing a condensed formula mean the same thing. Questions about those? All right. Now let's look at some different condensed formulas and line structures and practice going back and forth. So this is going to be that first type of condensed formula. And I'm going to ask you to draw a line structure for it. So if it helps you to first put this in more of a Lewis structure form, or just kind of put the carbons in a row in the right way first, that's fine. The goal is to ultimately get this in one of those line structures that just has the zigzags. Feel like you've got one, come put it up. We'll try, got a couple different ones if you have different ones. Yeah.
That is so ugly.
Sorry. Anybody have something different want to add here? What do you think? Does that look good? Issues? Excuse me. Sorry. Neither? Both? Good, bad? Good? Nobody got anything different? It's just flipped like upside down? Okay. Yeah, this is great. This is right. So we've got it's always a good practice, as we'll see when we start talking about naming too, to think about the longest connected chain of carbons. Put them in a row that way. So we've got 1, 2, 3, 4, 5. I could have gone 5 up here too, or started 1 up here. Doesn't matter. Just there's 5 in a row. And then down here, I can show those also. 1, 2, 3, 4, 5. And then there's another one coming off of number 2. So maybe we'll call that A. And another one coming off of number 4. That's B. So I've got one coming off of 2 and one coming off of 4. So if it all maps out, then that's got to be the right. Yeah.
Why is it CH3 put next to the CH number 4?
What do you mean?
Like,
Oh, yeah. I mean, it should be. But that's just how it's drawn sometimes for some reason or another. So we have to be able to interpret that and see that it actually means the same thing. But that's a good point. So really, it would be clearer and better if we were to draw this like this. Right? That's what you're talking about? Yeah, that's the same thing. That would be a better way to draw that condensed structure.
Draw it like that.
Yeah.
One line and one line.
Right. So there's a couple ways you could do this. So you can go like that, or you could draw it upside down. It doesn't matter which way you start your zigzag. So maybe you like to start zigzagging down instead of up. Get the same thing. Same structure. Okay. We're going to keep practicing this, but I want to, kind of in the context of this, also start talking about names. Yeah. Sure.
Okay, so the 2 line structures on the right, they also work for the one on the left?
Yeah. Those are all correct line structures. This one's really the same as this. It's just kind of smushed, but it means the same thing, so it still works. I should say, in general, in this class, we're going to be drawing a lot of stuff, as you probably gathered. I'm not going to grade you on your beauty of your drawings unless it's not clear, unless something is so crazily drawn that it makes it look like it's something else that's not a correct answer. So as long as you are conveying the correct chemical information and it's clear, you should be fine. So something like this would be fine because it's still really clear what that's showing, even though it looks kind of smushed. Okay, so let's talk about how to name these things. Has anybody ever done this stuff before, naming organic compounds? Yeah? All right, so we'll come back. Does anybody remember all the naming of the inorganic compounds from Gen Chem, like the salts and whether you have the parentheses and all that kind of stuff? Yeah. I think these names are a little easier, a little bit, but there's just less to memorize, and it's more just following the rules. But we'll see. Everybody has their own opinions about that. Okay. Yeah.
So this is like the note, right? Like not to be written on here. Like we can write it in
stuff
our.
wherever you want to write. Yeah.
So I guess my question is, you're always like in lectures and it's like on the chalkboard, right? Like that's how you're gonna convey your notes and everything.
As opposed to.
Like my other, like a PowerPoint or having
Right.
a projector already written down, just going through it.
Right.
Teachers are doing.
Yeah, I'll just kind of do it like this. I think because of the drawing, it's nice if we all draw together rather than just having it done. These will all be posted, by the way, also, so you can always get these on Blackboard, as well as the video that's recording all of this as we speak. Okay, so let's talk about naming alkanes. I'm going to kind of give you the rules first, and then we'll do the examples, and we'll look at how they work, and we'll talk about some of the things that we do need to actually memorize. So we're going to think about the names in 3 parts. It's going to look like 3rd grade English class for a second, but bear with me. Our names are going to have a prefix, the part at the beginning, and what we're going to call the parent or the parent chain. And then we're going to have a suffix at the end. So just like diagramming those English words in 3rd grade, you have your parent, your main root, you have your prefix and your suffix, and they mean different things. These names are set up in a similar way. And let me tell you a little bit about what each of these things tell us. So first of all, the parent chain, as you can imagine, that's going to be the most important part, and the part we're going to focus on first. And this is going to be the longest continuous chain of carbons. And actually, we'll get into this later, or ring. We'll get into what happens when they're connected in a ring. For now, the longest continuous chain of carbons. So you've got 6 carbons in a row, that's your parent chain. You've got 2 carbons in a row, that's your parent chain. There's just one of them, that's your parent chain. Whatever the longest carbons are, that's your parent chain. The suffix, the part at the end, tells us about something called the functional group. Which we'll get into later. We're not going to mess with that today. Right now, all of our suffixes are going to be anes because we're talking about the alkanes. Anybody know what an alkane is? Saturated with what? You're right. In some cases, in most cases. Yeah, with hydrogens. So it's more simply, an alkane is just a molecule that's made up of carbon and hydrogen with all single bonds. So that's kind of the simplest organic molecules, and that's what we're going to start with. Yeah, would you like me to write it down? Let's find some spot. So alkanes, only carbon and hydrogen. Only single bonds. So molecules with just carbon and hydrogen and just single bonds, which are most of the molecules we've dealt with today, except for those few that had some other stuff on them, like F or OH. Things like propane, butane. So then the other thing we haven't defined yet is the prefix. And the official word for what the prefix tells you about is substituents, and we'll get into what that means. But what that really just means is stuff hanging off the parent chain. So the beginning of the word, or the beginning of the name, is going to be all the parts that are just hanging off of that chain. We've got our main chain that ends in ane, and then all the stuff hanging off of it. So we're going to look at these molecules and find their names based on this. But to do that, we need to know a few basic starting names. So we can do that here. We'll make ourselves a little table. So if we've got just one carbon, what's the word we use for that? Anybody know? Close, and we'll get to that. It's actually meth. So if we have a molecule of just one carbon and nothing else at all, so it'd be CH4, that molecule is called methane. And we should put a little dash. So the alkane that just has one carbon is CH4, and the name is methane. This, by the way, is in your book on table 3.2, page 69, if you are following along or if you want to look this up. But we'll just list a few so we can use it for our practice in the next 15 minutes. We're not going to get too far here. So 2 is F. 3 is prop. 4 is bute. 5 is pent. 6 is hex. And 7 is hept. And 8 is oct. 9 is known. And 10 is dec. So if you've done some mathy type stuff, you'll notice the first 4 are kind of unusual, and the rest of them follow typical Latin-derived names for numbers of things, like hexagon, pentagon. If you've heard those sorts of things before, you might know those. But the first 4 are unique. So I'm going to draw a couple lines here just so we don't get lost. And get misaligned or something. So if we have a chain of carbons with 5 carbons and hydrogens everywhere, what would the name be? Pentane, right? So see how that works? Okay, so let's look at some names that get a little bit fancier than that. Everybody have this, by the way? If I can get that out of the way. Okay. All right, so we'll say, what is the name of this structure? So the rules are, we got to find that longest chain, figure out how many carbons are in it, and then find the stuff that's hanging off that biggest chain. So how many carbons are in the longest chain here? 6. So we've got 1, 2, 3, 4, 5, 6. And I like to just circle that parent chain just so I know what I'm talking about. If we have a 6-carbon parent chain, then we can write down hexane. That might not be the whole name. We'll have to check the prefix, but that is at least going to be part of the name for sure. If we see that 6-carbon parent chain, we know it's a hexane. Now, is anything hanging off that chain? Is there any other stuff that's not accounted for? There isn't, right? That is everything. So this molecule is just called hexane, and that's the name, and that's it. All right, so now let's look at what happens when there is some stuff hanging off. So we'll stick with our hexane, but we'll put an extra little line there. So we start the same way. We go, all right, what's the longest chain? It's hexane. 1, 2, 3, 4, 5, 6. And there it is. Hexane. But now not everything is accounted for, right? There's one more carbon up here that we have not included when we said hexane. So that becomes a hanging off thing, a substituent as it's called, a thing that's hanging off the main chain. And that gets named at the beginning of the name. So how many carbons are in that hanging off thing? Just one. So we go back to our chart and say, well, a one thing is called meth. It's not methane because it's not a chain by itself. It's a hanging off thing. So if it's a hanging off thing, we call it meth, and then we add YL. We call it methyl. So those substituents, those things hanging off, get a YL, and that's called a methyl substituent. And we stick that on to the beginning of the name right next to our main chain. So this becomes methylhexane, all one word. So are we done? Almost. We're almost done. There's one more thing that we have to do. We have to specify where that methyl is, because that methyl could be connected anywhere on that chain. And those would be different molecules. Those would be isomers. That's like when we took those things apart and put them on different spots. Those are different molecules. So we need to specify that. So which carbon in that chain is this methyl on? 2. So this becomes 2-methylhexane. And that is the full, complete, correct name. All right, let's keep going. So before we go on to another example, let's put all this into some rules that we can follow. Whoops, what did I just do? Whoops. Oh no. I hope I didn't just... where was it? Practice with larger organic structures. Well, you've got it written down, right? Something? Okay. That's all right. We'll have lots of other practice. That's not what I wanted to do. Let's try this again. Oh, we're not responding. Okay, there we go. Let's see. How much did we get? Not much. Okay, well, it's in the video if you need to go back to it. That's okay. We'll just start with our rules instead of our examples. And that table of stuff is in your book, so you don't really need that in the notes. Okay, so here's the things that we did if we think about what we did. What did we do first? Yeah, we identified that longest chain. So we figured out what's the longest number of connected carbons. And the book has a lot of good examples where it's not always just the straight across thing. Sometimes it's a weird mix of stuff. But whatever's connected, that counts as the longest chain. So this becomes your parent chain. Then what did we do? What? Yeah, we determined, I guess that I consider that part of identifying the longest chain. Then we found the substituents, or the things hanging off, after we figured the longest chain part. So we found the longest chain. We found the substituents. So then we need to number. We'll switch language here to use what the book uses, which is parent. Number the parent chain so that the substituents have the lowest possible numbers. Let me show you what that means. Let's say I wrote this molecule. So we go through our rules and we say the longest chain is this, right? How many carbons is that? 6. And then our substituent is here, right? And that's a 1 carbon substituent. So this is going to be methyl hexane, just like before. How are we going to number that chain? We have 2 choices. We can go left to right, or we can go right to left. Based on rule number 3, which way should we go? Right to left. Because if we went left to right, that methyl would be on carbon number 5. If we go right to left, it's on carbon number 2. So that's better based on this rule, yeah.
But if you do write number 5, is that still wrong?
That's wrong, yeah.
Why?
Because it violates the conventions of this naming. So the reason for that is, this is called, I don't know if you've seen this in the book, but it's called the IUPAC name, IUPAC, was this, organic molecules had this unfortunate tendency to just kind of be named after however they were discovered. Like if it was something in an ant, then it was called ant whatever, I don't know. But it became very confusing. So studying organic chemistry just meant you had to memorize thousands of names of different things that had no relation to each other. So at some point a long time ago, people came together and said, we need this standard way to always name things the same way. And so these are those conventions of how to name things always the same way. So when you say 2-methylhexane, everyone in the world knows what you're talking about. Every chemist speaking English in the world knows what you're talking about and can actually write down that structure. Right. And so that's the same thing. Yeah. It gives us a way of determining whether 2 structures are the same, which is another important thing we're going to get to in this chapter. If we look at 2 molecules, even though they're drawn differently, if they have the same names, they're actually the same. So the name then for this is the same as before, 2-methylhexane. All right, I'm kind of rushing through this, but we need to spend a little bit more time on this. So we'll have some more time on Wednesday. But to finish up here, let's try going to the next step and thinking about these rules. So let's go back up to this molecule right here that we drew. Let's think about how we might name it. So what do we do first? Okay, what's the longest chain? 6? Which 6? 5? Other ideas? 4, 5, 6? 5. So like here, right? Yeah. Okay, so then what do we do? Find the substituents. How many substituents are there here? There's 2. And how many carbons do they have each? 1. So these would also be methyl substituents, but now there's 2 of them. So we're getting ahead of ourselves here. So let's write down the parent name, which in this case would be pentane. And then we're going to put in our substituents. If there's 2 of them, we need to give it a prefix, kind of like back with the kind of naming that you did with in general chemistry. So we're going to call this dimethylpentane. And now we need to number that chain so we can figure out what numbers the methyl groups are on. Do we number left to right or right to left? Doesn't matter in this case because it's symmetrical, so it's going to be the same either way. So if we number this 1, 2, 3, 4, 5, which carbons do those methyl groups end up on? 2 and 4. So the way we express that in the name is by saying 2, 4, and then a dash, for dimethylpentane. And this tells us that we have a pentane or a 5-carbon chain with 2 methyl groups, and those methyl groups are on carbons 2 and 4. All right? Good so far? Okay. Now, I think this will probably be the last thing we do today. I'm going to write a name, and we're going to try to figure out what that structure should look like based on the name. Okay. So this name is going to be three ethyl 5 methyl heptane. So I've thrown in a couple of other little things here. So now this also has 2 substituents, but those substituents are not the same. So what do you think is the best way to go about writing a structure from a name? How would you start this one? Right, I would start with that parent chain. So let's draw a chain of how many carbons? 7. 1, 2, 3, 4, 5, 6, 7. Everybody get that one? Sometimes with line structures, it's easy to go 1. That's not right because you've already put down 2. So make sure you start counting 1 as soon as you put your pen down. 1, 2, 3, 4, 5, 6, 7. Okay, so then let's number that. Always helpful to put those numbers in because we all get mixed up counting sometimes, get things on the wrong spot. So what do you think we put on carbon number 5? Yeah, a methyl. So just 1 carbon is going to go on carbon number 5. And what do you think is happening over here on carbon number 3 then? There's 2, right. So we've got to remember the 2 is actually an ethyl, which is a 2-carbon substituent, so which is going to look like this. Not 2 separate lines. What would the 2 separate lines be? That would be that would be like a dimethyl, so it'd be a double. So it'd actually be a trimethyl because it would be the 3rd one. So we need to make sure that we have our substituents accounted for. There's our methyl, and there's our ethyl, our 2-carbon ethyl substituent. Yes. So the substituents will also have ill, butyl. Yep. Right. It becomes less likely to have those bigger ones because if you have something big like that, chances are it's going to be part of the parent chain. If you had a pentyl substituent, you'd need a really big parent chain to have that coming off of it. All right, so we will get more into this on Wednesday. We should have a little time besides lab. We're going to be doing the what lab is it chromatography? Okay. Okay, so we should have some time with that to practice this a little bit. Our first official quiz, this was just a pretend quiz, our first official quiz will be next Monday on all this stuff so far. And then our exam, which is in 2 weeks from Wednesday, we'll cover all this stuff plus what we do next week as well. So if you want to kind of keep on top of things, we haven't finished talking about chapter 3 in here yet, but that will definitely be on that first exam. So keep working your way through chapter 3. You should be able to do most of it on your own now that we've introduced it. We'll also be getting through chapter 4 before the exam. And so that will be that first exam. That's very nice. So please take your models apart and put them away. And I will see you on Wednesday.